After learning the three algorithms, FIFO, optimal, and LRU, let's move on to implementation. So how do we implement FIFO? Apparently, FIFO is very easy to implement. What we need to have is just a queue of page numbers. But unfortunately, because of the Belady's anomaly, probably we don't want to implement FIFO. So our choice is either optimal or least recently used. But unfortunately, optimal is impossible to implement because the algorithm must predict into future memory references of your process. So the only choice at this point is just implementation of LRU. By the way, both optimal and LRU are under a class of algorithm known as stack algorithm. So what is a stack algorithm? Mathematically, we can express the stack algorithm using this set relationship. So if Pn is a set of pages resident in RAM when process is allocated n frames, the stack algorithms has this property that pages which is resident when the process is allocated n frames is a subset of pages when we increase the allocation frame by some number k. So what is the practical implication of this property? That means as we increase our frame allocation from n to a bigger number, we never lose any pages. So this is a good thing about stack algorithm. Let's look at how LRU behaves like a stack algorithm. So at the top of the page, you see how 3 frames are allocated to your process, and the bottom of the page is where we allocate 4 frames. And if you compare vertically, at each time, you can see that the set of pages in 3 frames is always a subset of pages in 4 frames. So probably if you compare at time 4, so the set of pages resident when we allocate 3 frames is page 2, 0, and 1. And when we allocate 4 frames, at that point, the resident pages is 7, 0, 1, 2. And we can see that 2, 0, 1 is a subset of 7, 0, 1, 2. And if you look at the rest of resident pages, you will see the property that the subset of pages here is always a subset of the resident pages here. So this is just to show you that LRU is really a stack algorithm. So how do we implement LRU? Just to remind you, when we talk about LRU, the algorithm selects the victim page by looking at the nearest backward distance among the resident pages and then pick the one that has the highest backward distance. So for instance, when we are handling the page fault for 3, the current resident pages are 2, 0, 1, and if you look back from this time, then the backward distance for 2 is this distance, and the backward distance for 0 is that distance, and the backward distance for 1 is that distance. So at this point, we know that the page that has the largest backward distance is page 1. That's why we replace page 1 with page 3. The victim page is page 1. Unfortunately, using backward distance, the algorithm must keep track of the previous memory references of a process, and that may take up space. So as an alternative, instead of using distance, we can convert the selection algorithm to use time. So now we annotate the diagram with the execution time of your process, 20, 21, all the way to 25. So let's say at time 21, page 0 is reference, and that's why you see the entry for reference time of 0 is 21. but page 7 is first referenced at time 20. That's why you see reference time of 7 is 20. So if you keep going, so now page 1 is referenced at time 1. So in addition to the current 2 records in our page table, we add a new record for reference time of 1, which is at time 22. Now, how do we handle the page fault for page 2? So when we look at the reference time of the 3 pages 701, we notice that the reference time of page 7 is the lowest. So this is the candidate for replacement. From this example, we can see that the criteria for selecting the victim page can now be expressed in terms of time. So instead of looking for the highest among the nearest backward distance, we now want to look for the lowest time to the most recent reference. So when a new page is loaded to RAM, page 2, in this example, we do have to update the reference time of that page. So that's why you see reference time of 2 is 23. And the next page reference is page 0. Every time a page is referenced, we have to update the reference time to the current execution time of the process. So here, page 0 is referenced again at time 24. That's why you see reference time of 0 is updated from 21 to 24, because this is the most recent time when page 0 is referenced. So we're going to look at again how do we handle page fault of 3. So currently the resident pages are 2, 0, and 1, and if you look at the reference time of each, we can see that page 1 has the lowest value, and that's why we replace page 1 with page 3. In conclusion, now it is possible to implement the LRU algorithm using timestamp. Instead of backward distance, we can keep track of the reference time of that page. So because reference time is just a single number, we don't have to keep like a list of previous memory references to each page. So then, do we have to use the actual timestamp of the computer? Apparently we don't have to. The important thing is we do need to know which page has the lowest reference time. So we don't have to use the actual timestamp from the CPU. We can just use some relative number. So that's why another idea for implementing this algorithm is to use a linked list of page numbers. And every time a page is referenced, then we're gonna move that page to the beginning of the list. So what is the side effect of this self-adjusting linked list? That means now pages which are recently referenced will stay at the beginning of the list, and pages which are least referenced will stay at the end of the list. So at page fault time, the victim page will be the one at the end of the list. So using relative timestamp requires updating a linked list by moving elements around inside the linked list. But we do want to look for something that can be done in hardware very easily. So we're going to look at several approximation technique to make sure that our hardware is not too expensive. So the first simple approximation is just use one bit, and we're gonna call this bit the reference bit or the R bit. So how does it work? And again, as soon as we move into implementation, we do need to see how the hardware and software work together. And remember the recurring theme that we have been seeing since first week of class: features in operating system only possible when we get support from the hardware. So the idea of using this one bit, every time a page is referenced by your MMU, then the MMU will automatically set the R bit to 1. And at page fault interrupt handling, the operating system will look for pages with R bit equal to 0. Why? Because when a page is never referenced, the R bit will stay 0. But the disadvantage of this technique is that we cannot distinguish whether a page was referenced 5 milliseconds ago or 20 milliseconds ago. Using 1-bit reference seems to work, but the system cannot tell whether a particular page was referenced like 10 milliseconds ago or 20 milliseconds ago. In order to solve this issue, we can add a k-bit history tag to the hardware. Again, this is always a cooperation between hardware and software. So every time a particular page is referenced by the hardware, then the hardware will set the reference bit to 1. Now, the software part is to periodically check the reference bit and then push that bit into the k-bit history, and after that, the software will reset the reference bit. And then the victim selection algorithm will look for a page whose k-bit value is the lowest. So let's look at an example where we use an 8-bit history tag. In addition to the reference bit, the system will keep an 8-bit history tag for each page table entry. And again, remember, the hardware will set this bit to 1 whenever a particular page is referenced. And then periodically, the operating system will push this bit into the tag. So then the oldest reference history will stay on the rightmost bit, and then the newest reference history will stay in the leftmost bit. And then after the operating system injects that bit into the tag, the reference bit is again reset to 0. So now let's say the system will inspect the reference bit, let's say every 100 milliseconds. Using this number, this bit will tell us what happened in the last 100 milliseconds. This bit will tell us what happened in the last 200 milliseconds, and so on and so forth. So now let's compare two different values of history tags. This bit pattern tells us that the page was referenced 200 milliseconds ago, 300 milliseconds ago, and 800 milliseconds ago. And it was not referenced in the last 100 milliseconds. But the second pattern here tells us that this page was referenced 400 milliseconds ago and 700 milliseconds ago. So between the two pages, we should remove this page because this page was least recently used compared to this page. If you compare the two values in binary, we can see that the smallest tag should be the candidate to be replaced.